over the last 10 days, we have tried to figure out what are the degrees of freedom that you find on the worksheet of a string. So we did our gauge fixing. We studied the property of free scalars on the cylinder, and so on and so forth. So let's put the pieces together. So we saw that after we go in a gauge where the metric is flat on the cylinder, and we use complex coordinates, what we find living on the worksheet of the strings are a bunch of scalar fields which describe the motion of the string in spacetime, and a bunch of ghosts. It comes from the gauge fixing. So there is some sort of an action. And everything is free. You know, nice quadratic action and extremely computable. So this action has all sorts of symmetries. There are translations in space-time. There are Lorentz transformations. There is because number symmetry, which is more or less a symmetry. It's a bit anomalous, but still useful. So it rotates the C's and the B's in opposite direction. And finally, because of the gauge fixing, we are supposed to have a BRST symmetry. It is supposed to act on the matter fields as a diffeomorphism by whose parameters are the C ghosts, which means to act on the B field, on the B ghosts, by shifting them by the total stress tensor. And on the C ghost, I think something like that, at least classically. Now, these symmetries are pretty trivial to see in the action. This symmetry is a little bit tricky. I mean, it takes a bit of patience to go through the algebra. If you feel like doing it, feel free. But you can roughly see, you transform the x's, you get something like something xxc, roughly. You transform your b, you get something else like xxc, but you also get something like bcc, because the stress tensor includes various pieces. I don't remember all the signs and numbers, but it was roughly something like that. And then that extra, those BCC are going to cancel out against the transformation of C. Now, all of these symmetries are associated to currents. I think you have seen the Nether theorem in one of the tutorials. So, for example, the translations are associated to currents that look like this. These are the two components of the current. Perhaps, right. So these are J, Z, JZ bar. Say. And for translations, these are actually separately conserved. So in a sense, the translations in two-dimensional, this two-dimensional free field theory split into two transformations which shift independently the left and right, the holomorphic and anti-holomorphic parts of X. Now, in flat space, this is not very, very important. Okay, at least it's not very, this extra symmetry is pretty difficult to see. It doesn't really act on anything interesting because there is, after all, the quantum numbers for these symmetries are the momentum. And we saw that roughly the momentum for the holomorphic and anti-holomorphic parts is the same. I mean, we define some zero modes at some point of the scalar field, but they coincided with the momentum. But actually, when you start studying string theory, more interesting work, target space, like study compactifications of string theory, then the existence of two separate conserved symmetries would become important. Lorentz transformations, I think the currents look like these. And actually, these ones are not separately conserved. This guy was holomorphic, but this is not holomorphic by itself. So rotations are just standard. The Gauss number symmetry, the current was something like this, BC or CB, C bar, B bar. Now the current for a BRST symmetry is a bit longer to write down. It's straightforward to get it in principle. You just apply another procedure to this transformation and this action. I'm not going to use the explicit form of this current. So I'm not going to, the coefficients I'm going to write on the board are not the correct ones. They're going to be all 1, and they're probably 1/2, so -1 or whatever. Find them on the textbook. Roughly, it looks like this, classically. When you try to define it quantum mechanically, there are some, there is some point splitting to do. You get some extra corrections. Okay. With Tx, I mean just the part of the stress tensor which comes from the scalar fields. Okay. Okay, this is a pretty ugly-looking object. It's clearly conserved because it's made out of holomorphic things. But what we really care about is that the charge that you get out of this current should be nilpotent. So there is a BRST charge. Usually it's denoted like this. Sometimes I'll denote it just as Q. And you want this BRST charge to square to 0. Mm-hmm.
What do you mean by Tx?
Sorry?
What do you mean?
Oh, Tx is just this.
Oh, okay.
See, now if we want to study what we want to do, that is, so one of the things we wanted to do was to understand the spectrum of strings, the spectrum of string theory. We did it a bit by hand last week. And in principle, it can be done properly by using the BRST symmetry, meaning we start with the Hilbert space of this theory. And inside this Hilbert space, we are looking for Q closed states. So which means states made out of matter, some states which are annihilated by Q. And then the spectrum of string theory is supposed to be the space of Q-closed operators, states, over the spectrum of Q exact states. So in order to describe the Q-closed states, the Q-exact states, we need to know how the BRST symmetry acts on states. Yeah, it does give you the action of on operators, on fields. But once you have the conserved currents, there is a standard way to find the action of a symmetry over states. So pretty much, so if you have a cylinder, you have any conserved current, this component J sigma and J tau. Tau is Euclidean time, sigma space. Then a way to get a charge is by integrating J tau in the sigma. So this is the standard way to get the conserved charge out of a conserved current. The reason this is conserved is just that you can do the tau here, bring it in, rewrite this as the sigma J sigma, and then integrate by parts to get 0. So if you apply to the BRST symmetry, you're going to get a specific expression. Right? This is telling you that BRST symmetry is basically the 0 Fourier mode of this BRST current. So in principle, to find it, you get just an isomorphic expression, expand it in Fourier modes after having done your point split appropriate regularizations. Get the 0 mode, do the same thing for that, get the 0 mode, and you get your expression for the BRST charge. It's a pretty cumbersome expression. Okay. Roughly, there is something like this. And then some stuff involving ghosts. And probably also something linear. You see. I'm not going to write in detail what that is. But really, you can get a lot of mileage just from the basic relation. Which relates the B field and the stress tensor. For example, let me show you some example of the consequences of that. Okay, for example, if you, from the explicit expression, in principle, you can check the q square equal to 0 if and only if there were 26 free scalars. That's an extremely tedious calculation. On the other hand, you can also simply observe that q BRST has commuted the stress tensor as a consequence of this relation, and q square equal to 0. On the other hand, we know that the commutation between L and B so if you apply a commutation with Q, sorry, this would be an anti-commutator. And sorry, I wrote it commutator, but because I really meant anti-commutator. These are true Grassmann odd objects. So here I can bring this in. It kills L and transforms B into L. So you see that if you really want to have a BRST symmetry for which this is true and which is important, then it must be that your total Virasoro algebra has no central charge.
When you write Lx of minus n is just the Virasoro mode for the export?
That's right. That's right.
And in these commutation relations, Ln is the Virasoro mode of the full BRST?
That's right.
Okay.
That's right. So this BCC, this CCB is cooked up in such a way that when you commute it to B, it gives you the Fourier mode of that. Okay. Now, finding all the Q-closed states, modulo Q-exact states inside the Hilbert space, and proving that the list that you have is all that there is actually another extremely tedious exercise. But there is, so it's done in Polchinski, I think, in detail. But what you really need to know is that there is a no-ghost theorem. So some people have computed the cohomology of this BRST charge. So the cohomology is known, and the cohomology has a nice, well-defined positive inner product. So by restricting to Q-closed doped states and dividing away Q-exact ones, we get rid of all the null states. So although this theory has ghosts, so this Hilbert space does not have a positive definite inner product. So I probably shouldn't even call it a Hilbert space. After I restrict to this and divide by the null states, I get something nice and positive definite. If the signature of space-time is 1,25. This is another kind of entertaining fact that, you know, there is no Euclidean string theory or no string theory in 2,24 signature or whatever. At least it does not have a, no, okay, maybe it's not a totally useful statement in the sense that the notion of positive inner product, unitarity, and so on are notions that are intrinsically appropriate for Lorentz signature, 1 comma d minus 1. So the fact that you don't find them unless you have that signature perhaps is not as surprising. But
Is that result 125 independent of our signature of our worksheet? Or it depends on the
that's right. Actually, so the matter of the signature of the worksheet is another of those intricate matters. And you might very well wonder, why did it work with Euclidean worksheets? Why didn't we work with Lorentzian worksheets? It's a fair question. And it will come bite us in the next lecture, indeed. The simplest answer is that only with Euclidean signature we know how to make these smooth junctions between tubes. Lorentz signature tubes will not have such nice, smooth junctions. Now, the restriction on Euclidean signature is less constraining than it might seem. In a sense, you can always do once you get a final result on how to compute the amplitudes, there will be some integral over the possible shapes of these worksheets, the intrinsic shape of this worksheet, the intrinsic geometry of these worksheets. And in principle, I believe that if you do analytic continuation in that, so there is a certain integral, you can sort of analytically continue that integral, move it around in a complexified space. And I think by doing that, you can actually do whatever you would have done by using a Lorentzian worksheet. So I think that there is actually true that you don't lose information by looking at Euclidean worksheets. Of course, another answer I could say is that I could give is that at least at the end it works. Meaning, if I use Euclidean worksheets, I get some scattering amplitudes that satisfy all the axioms that scattering amplitudes have to satisfy. They behave like quantum field theory scattering amplitudes at low energy. They have unitarity, etc. So you can always give an a posteriori justification. But yeah, it is actually an interesting matter.
Peter, I have another question.
Yes.
So if you can repeat, the no-ghost theorem says there are no null states in the...
No, that's right. No negative norm states.
No negative norm states.
And no null states too. The inner product is positive definite.
How about ghost states in the sense of states that only have B and C modes in them? Are these...
No, so they're not in the cohomology. So even if you can find some that are Q closed, they always turn out to be Q exact.
So you also get rid of them?
Yes. Yes. Right, so now in a sense, I don't care about describing the whole BRST cohomology. But let's just focus on the states, which, in a sense, come naturally into the problem, meaning we started, before gauge fixing, we had some states of these worksheets coming in. So some states of the matter fields. Then we put in the ghosts. But it's, the states that we had should remain roughly the same. So the ghost will sit in the ground states, and the matter will do whatever it was doing before we gauge fixed, roughly speaking. So the states that are interesting to look at least to start with, are states in this product of two Hilbert spaces. So we look for some states inside the Hilbert space of the three bosons. And look for physical states for the string of this form. But this is the ground state we introduced at some point in the last lecture. Remember, this ground state was written as C1, C1 bar, 0, where the 0 was a BRST invariant state. Now, because they're sitting in their ground states, these states have the property that they are killed by Bn for positive n. So let's substitute Q on this identity. Okay, and use the anti-commutation relations. So we learned that if you're looking for a physical state of this form, so something is annihilated by QBRT, it better also be killed by Ln, the positive n, positive or 0. Now, Ln acting on this state is the matter, the X part of the Ln's acting on the matter field excitations, plus L of the ghost acting on this ground state. And L of the ghost acting on the ground state gives actually -1. So this the equation for the physical states, I mean, we see that the physical states, all the physical states of this form have to satisfy L0, x minus 1, v equal to 0, and Ln v equal to 0 for positive n. So these are the conditions we saw last week when we did things by hand. With a little bit more work, you can show that the converse is true. That if these conditions are true, then this is indeed Q closed. It takes more work to show that the null states are of the form the states of the form the states of this form are null. But it can be shown. It's not a straightforward calculation in the sense I cannot just tell you, okay, this is equal QBRST or something obvious. So this can be written as QBRST or B minus n. Sorry, this is a minus n. T prime tensor G plus extra stuff involving ghosts. The extra stuff can be built systematically, but it's a tedious operation.
How does QBRST commute with C, with the C? Do they just want to commute?
QC gives you C to C.
Do we have it? Sorry.
Over here. Right. Sorry, so there is a little bit of algebraic work to do to get to these statements, and it's part of this of the work for this no-ghost theorem.
So Q on G is 0. Is that true?
Mm-hmm.
Q on G?
That's right. Q on G, that's correct. That's a good QBRST on G gives C0 G, which remember was the other ground state. See, there is only one Q commutes with L. Right? particularly commutes with L naught. So Q does not change the level, the energy of your state. It commutes with the energy. It's conserved charge. And when it acts on the ground state, all that it could have given you was the other ground state. And it does. So now the BRST cohomology, these states do not exhaust all the BRST cohomology. They exhaust the BRST cohomology because number is 0. Because number, well, at the Gauss number of the ground state, which is -1/2, I guess. So this is the cohomology at Gauss number 1/2. And in a sense, these are the natural states to insert in a string theory scattering amplitude. I think discussing the other pieces of the cohomology would just bring us far from what we want to actually do. Essentially, there is a second copy of the cohomology at Gauss number +1/2, which is essentially the dual states of these ones, the ones that people put as they're like the brass and the cats. And then there is a handful of other peculiar states, which has to do with the symmetries of the theory. Which leave it more peculiar process of Gauss number. Okay. So, fine. Starting from here, you just repeat the discussion we had last week. We already know that these conditions automatically tell us that the string spectrum has a tachyon, a graviton, a couple other massless fields, and then infinite towers of massive fields. What I would really like to get to over the next few lectures is to compute the scattering amplitude between these states. And to do that, we need a little bit more a few more tools. They're all tools about two-dimensional field theory, free field theory. But so they're not conceptually very difficult. And again, they're facts about quantum field theory, which will come out useful to you independently if you want to study string theory or not. Unfortunately, they are all things that you would learn if you had done some course in conformal field theory before this. But you didn't, so. So now, it's clear that before doing scattering amplitudes, okay, you could say, okay, fine, because the spectrum of string theory. We found some spin 2 massless state. But even when I call it a graviton, it's just a name, right? Unless you see why the scattering amplitudes of string theory reproduce the scattering amplitudes of quantum field theory. It cannot be, there is no way to understand why this is actually a graviton, a true graviton, why string theory is really a theory of quantum gravity. So to understand that, we need to keep going. So I would like to devote the rest of the lecture to understanding something called the state operator map. The state operator map is a correspondence between states of a conformal field theory and operators of a conformal field theory. Now, I didn't tell you what a conformal field theory is, so let me step back one more step. So start from some While invariant theory, like the theory of the scalar field. So we saw that whenever you have wild symmetry, you can do changes of coordinates. If you work with complex coordinates, you can do changes of coordinates which are holomorphic. And then use the wild transformation to bring the metric back to be flat. So it's sort of change of coordinate will send the z bar to something like that. And then you can apply wild transformation to go back to the flat metric. Okay. So a conformal transformation, in general, in any dimension, is defined as a diffeomorphism whose effect on the metric can be undone by wild transformation. Okay? So whenever you have wild invariant theory in any dimensions, you can go. If you start from the theory of flat space, you do a diffeomorphism that makes the metric not flat. If you can make it back flat by a wild transformation, so that you get a symmetry of the theory of flat space, then the diffeomorphism is called conformal transformation. And the theory is also called the conformal field theory. It's a theory which is invariant under conformal transformations. So in a sense, conformal field theory, the notion of conformal field theory is a little bit more restrictive than wild invariant theory. But it's already powerful enough to be rather interesting. Conformal field theories, for various reasons, every time you have a quantum field theory which is invariant under rescaling of spacetime, scale transformations, it usually turns out to be also conformal invariant. It's almost a theorem with some assumptions. So conformal field theories are interesting and useful every time you have a situation where your setup becomes scale invariant. The typical situation is that you have, for example, some RG flow. You have some theory, quantum field theory. You look at it at farther distances, making it at lower and lower energies. And if you manage to tune your parameter in such a way that it remains interesting at all scales, then what's left after this infinite rescaling is something that is invariant under scale transformation, and usually also conformal. So conformal field theories appear in condensed matter physics, in theoretical field physics, very often as a low energy description of some interesting system, some system tuned as some phase transition, something like that. And the state operator map is a property that all of these theories have. And it's related to the fact that flat space is conformal equivalent, can be transformed into a cylinder by a conformal transformation. So what does it mean? Let's do it in 2 dimensions, although things are valid in higher dimensions too. Consider this transformation, where S is the coordinate we are using on the cylinder. Okay? So it's something like this. So what happens to the cylinder under this map? Well, now here my drawing skills will be tested. So the lines of fixed tau become lines of fixed radius in the plane. The infinite past is mapped to the origin. And the infinite future is mapped to large distances. Translations along the cylinder are mapped to scale transformations, dilatations in the plane. So if I give a correlation function on the cylinder, and you do this transformation, you might wonder, what do I get on the plane? Now let me just give some details about the wild transformation, which might be instructive too. So if I start with ds, dz, dz bar, ds bar, this becomes dz bar over c squared. So the wild transformation, which relates the cylinder and the plane, is a transformation which blows up a neighborhood of the origin. So it's able to transform a neighborhood of a point into a semi-infinite tube. So you can imagine this is going to be useful when we study scattering amplitude of string theory, because we had to deal with this sort of very complicated surfaces with these semi-infinite tubes coming out. But this should show you that if you use the correct wild transformation, you can actually map these to a sphere with 4 special points. Your wild transformation can transform these semi-infinite tubes into neighborhoods of points. So that's why we need this state operator map. I need to be able to compute expectation values of some quantum field, of some conformal field theory on a funny manifold like that. That's hard. But I'll be able to transform the problem into correlation functions on a sphere, which, as you will see, is actually easy. So let's look at some examples. We computed a lot of correlation functions on the cylinder. So let's see what can we do with them. For example, we computed this. Now, because here we have the derivative with respect of s, it's quite clear that if you want to get something that behaves well in the plane, you better put a Jacobian there. So what is that? The Jacobians themselves are e to the minus s and e to the minus s prime. And then there is the correlation function, which we computed, which look like this. And once you transform it in terms of the coordinates on the plane, it looks very simple. Indeed, this actually coincides with the expectation value, with the correlation function on the plane of dz(x). So this is a straightforward calculation. It's just a Gaussian integral. I invite you to do it. To show just from the path integral that this equals this. This is the second derivative of the Green's function for the free scalar. Now we just learned that indeed things are working. I'm doing a conformal transformation, and I'm relating a correlation function on the cylinder to a correlation function on the plane. But we'll learn something more. Here we put the vacuum, and here we're getting a plane with nothing special going on at the origin. So one of the first elements of the state operator map is that if you place the state 0 far in the past, the vacuum state far in the past, is like inserting nothing, like doing nothing at the origin. So it's like inserting 1 at the origin. See, because strictly speaking, the cylinder is not mapped to the plane. The cylinder is mapped to the plane minus the origin. So in principle, you could get a path integral on the plane with something funny done at the origin. But here we see that if we put the vacuum, you actually do nothing funny at the origin. Yes?
Can you explain again why the 2-point function on the plane corresponds to like not having a state in there at all?
It's not much about the 2-point function. So here I did 2-point function, but I could have done something more complicated. So I could have taken any number of these currents in the correlation function. And I claim that this will be the same as the correlation function on the plane. With nothing at the origin. Now, what if I didn't put the vacuum? Well, how do I get other states? Suppose I want to know what happens if instead of the vacuum, I put here a minus 1 acting on the vacuum. Well, I can write a minus 1 acting on the vacuum actually as the limit as tau goes to minus infinity of e to the minus s ds x s acting on the vacuum. You can check this statement from the model expansion of x, which means that I can just use this, bring one of the fields to minus infinity, and see what happens here. Well, what happens here? It just means that one of the fields ends up being at the origin. So we'll learn another piece of dictionary. If I want to put a minus 1 in the past, is the same inserting the x at the origin. We can keep going. You know, a minus 2 is going to be the same as the x, the square x. I don't know. A minus 1 squared is going to be the same as the x dx. Probably normal order, something like that, etc. So you establish progressively you establish a full dictionary. There are many entries. On one side, you have states on the cylinder that you can set in the past. On the other side, you have operators. And this is actually one-to-one.
When you put the triple line, you're not defining it that way, right?
No, I'm just saying inserting these on this side is the same as.
I'm just wondering what the notation, it just looks like you're defining this to be equal, but that's not the case, right?
No, I'm not defining it.
It's actually equal.
Right, it's the result of a calculation. I compute both, and they're the same.
Right.
I think the question was, when we write a correlator on,
yes.
on the plane, don't we have in mind some vacuum also?
Not really. It's the result of a path integral. So you could say that I mean, you see, we're working in Euclidean coordinates. So, okay, you could say that I want to imagine that this direction on the plane is Euclidean time. So I put far in the past the vacuum on the line, and far in the future the vacuum on the line. You could call that 0, but it's a very different meaning from that 0, which was the vacuum on the circle. But I don't like doing it because, after all, who told you that this was time, right? The way these sort of things are computed is by a path integral. You integrate over all the maps from your plane into your the scalar field. Mm-hmm.
Sorry, couldn't you instead do radial quantization on the plane and then have a vacuum in the origin? Then you would have a map. Yeah, this is more or less the same.
But you know, what does radial quantization actually mean? Radial quantization means doing a quantization using as a Hamiltonian the scale transformations. So this is something that only works for a conformal theory, right?
Okay.
And if it works for a conformal theory, you can just as well go on the cylinder. So radial quantization is not something extra which happens to be equal to that. It's literally that. So that's why I didn't introduce it in the lectures, because it's so when you see radial quantization, what it means essentially is doing things on the cylinder while thinking about the cylinder as a plane. So you're I don't have time to do it now, but perhaps one of the tutorials exercises. Sorry. So here we did it for the currents. Okay. And of course, so this can be extended to all the operators which are built out of the currents. So I know the stress tensor. For example, it's true that if I put L minus 2 on the vacuum on one side, is the same as inserting the stress tensor at the origin. And so as I was mentioning, the existence of this sort of map correspondence between states and operators for conformal field theory is universal. It's true for every conformal field theories. Here we're discovering it for the free field theory, a step at a time. Now, we are clearly not done, because there are a lot of other states in the hyperspace, right? We have not said anything about the momentum modes. So, question, is there an operator which, inserted in the origin, will mimic the effect of a momentum mode in the past? And the next lecture, I'm going to describe this operator in detail. It's called the vertex operator, and it's written like that, which is a little bit unconventional looking. I guess until now you've seen only things that are made as polynomials of a scalar field. These sort of things can exist and make sense in 2 dimensions because the scalar field is dimensionless in 2 dimensions. Because it's dimensional, it makes sense to have functions of it, exponentiate it. So we'll try to learn how to define this in the next lecture. Once we define this, then we can have a complete state operator map. We can find an operator which inserted at a point is equivalent to having, after a while transformation, a long tube with some given state inserted here. So we'll be able to take the picture with 4 states inserted in the external legs and map it to picture like that with 4 operators inserted on the sphere. Okay, I think this is more or less all I should say today. Yes. But as an exercise, start familiarizing yourself with exponentials of things. What does that mean? Just do quantum mechanics. So try to see what you can learn by thinking about operators of the form this form. How do they multiply, for example? Can you compute this?